Good morning all. So last class we have discussed few numericals on sampling theorem. Today also we will discuss few numericals on sampling theorem, and then we will jump into the time division multiplexing. So today is 12. So let me take one question. So a low pass signal low pass signal x of t has a spectrum. Spectrum means its Fourier transform. Okay, x of f given by a relation x of f is equals to 1 minus mod f divided by 200, where mod f less than 200 and 0 otherwise. Okay. Here we need to sketch bit 1, sketch the sample spectrum. Means x of t need to be sampled and the spectrum we need to represent. Sample spectrum, that is x del of f. For sampling for the frequency mod frequency f less than 200 Hz, if x of t is ideally sampled at a rate of fs is equals to 300 Hz. Okay, and then the second point, repeat the above condition or above statement if the sampling frequency is 400 Hz. Okay, so these are the two things which is given to us. One, x of t is given, done, where its spectrum is x of f is 1 minus mod f divided by 200, where mod f is lies between minus 200 to plus 200. This indicates that f can be positive, it can be negative. First we need to identify the sample spectrum x del f. Okay, x del of f means it is a spectrum of the sample signal. Means this is a sampler. When you provide x of t, the sampler output will become x del of t. Done. Here x of t is Fourier transform whose value is given x of f is equals to 1 minus mod f divided by 200 for mod f less than 200 and 0 otherwise. So this is the condition is given, and we need to represent this x del of t to x del of f. Okay, and x del of f, and that to be sampled at a rate of 300 Hz. Okay, how to represent this? Very simple. So x del of f is equals to fs, general equation I am writing, minus infinite to infinite x of f minus n fs. Done. So this is my general representation. So here fs is how much? Fs is 300. So I will substitute 300. N is equals to minus infinite to infinite x of f minus n into fs. That means it is 300n. Okay. Now if you substitute n is equals to plus 1, that means f minus 300 it will come, and if you substitute n is minus 1, then it will come as f plus 300 it will come. Okay, that we need to represent. Okay, so and one more important thing, your x of f is a band limited to 200 Hz to the minus 200. So this is x of f. And first case 1, if fs is equals to 300 Hz. For this, the condition is this much. So what will be its spectrum? Let's see. So first of all, when n is equals to 0, you will identify this particular signal x of f. So first let me draw x of f. So this is 200 Hz, this is minus 200 Hz. Done. Next, if n is equals to plus 1, f minus 300 it will come. Done. And if n is equals to minus 1, f plus 300 it will come. That means the center frequency will be at 300 and another one is at minus 300. Then similarly, when n is equals to 2, you can find out f minus 600, f plus 600. Okay, and that too, the band limited is 300 is given. So now okay, so why I have drawn this one? Because this is the 300. First n is equals to 1 point I am considering, because as it is given, mod f is less than 200. So that is the band limiter of a particular modulating signal. Done. And it is shifted. So here you can see that it is around 500 and this is minus 500. So when you take minus 200 to 500, your band limited must be 300. How? Because here sampling frequency is given as how much? It is given as 300 Hz. So this is the particular spectrum. Now if you are sampling at a rate of fs which is 300 Hz, that means the spectrum of this component overlap with respect to the message component. So when at a recovery end, this part of information is also included. Up to this much it is included. That means it includes other information which can act as a noise for our message component, and due to which the message signal gets deteriorated and we cannot recover the original message component. Okay. And one more important thing. Now, here the bandwidth need to be satisfied. So what is the bandwidth? The bandwidth is, as my modulating signal is 200 Hz. So what is the bandwidth of a modulated signal? The bandwidth is 2 into 200, that is 400. Okay. So here you can see, if you are considering this point is 100 Hz. Okay, and this part is 500 Hz. So lower limit and final limit, if you take, it will become 400 Hz. Similarly, this is minus 100 and this is plus minus 500. So that is 400 Hz. This must satisfy this. So your bandwidth of a particular sampled signal is also 400. So if it is 400, that means if it is centered to this 300, if it is n is equals to 1, f minus 300. 300 is one position, minus 300 is one position. So that will act as a center frequency, but the side bands must have a difference of 2 to 100. 2 to 200 hertz right hand side, 200 hertz left hand side, so that the total bandwidth will become as a 400 hertz. Okay, so that is also come into picture. So here what it indicates, here the sampling frequency is less than the modulated or the sampled signal bandwidth. So here as it is given, sampling frequency is 300 hertz. Okay, but actually what should be my sampling frequency for the given signal? It must be twice of f max. Okay, so what is the f max? What is the maximum frequency available in my modulating signal? The available modulating signal is 200. So that means the sampling frequency must be 400 so that the message signal can be recovered easily. But as in the question it is given fs is equals to 300, that means the sampling frequency what it is given is less than what it is required. The required is 400 hertz, but the given is 300 hertz, due to which this sort of interference will be generated, overlapping of a spectrum will be generated. Okay, and this is called as a aliasing effect. Due to aliasing effect, we cannot recover the original modulating signal or the message component. Okay, so this is the first case. Second, now if the sampling frequency is 400 hertz, okay, as per the given statement, repeat the above statement if it is sampled at 400 hertz. Yes, now if it is 400 hertz, we can easily extract our information. How? Let's see. Now fs is equals to this. So I will write x del of f is equals to fs summation n is equals to minus infinity to infinity x of f minus s. So here I will substitute, it is 400 summation n is equals to minus infinity to infinity x of f minus 400 into n. Now if you substitute n value as positive, n value as negative or 0, you will get a spectrum. If n is equals to 0, that means this is the spectrum. Okay. Now if this is the spectrum, what is the band limited of this signal? The band limited of this signal is 200. Okay, 200 hertz. This is x del of f. Done. Similarly, if n is equals to 1, that means 400 will come into picture, and then n is equals to minus 1 plus 400 will come into picture. So in that case, your center frequency will be 400 and your spectrum will be like this. So this is 400 minus 400 and your spectrum will touches with each other. All these spectrums are having same bandwidth. So this is 200, this is 600 and this is minus 600, this is minus 400. So it satisfies the bandwidth. So 600 to 200, what is the bandwidth? 400, yes, it satisfied. So this is the resultant of a particular x of t if it is sampled at a rate of 400 hertz. If it is sampled at a rate of 400 hertz, its required sampled signal is 2 into f max. Okay, which is equals to 400. That means it is meeting that what is the Nyquist rate required to sample my x of t. If it is meeting, if it is equal, that means the spectrum won't overlap with each other, rather than they will just touch with each other. End point of one spectrum is same as the starting point of another spectrum. Okay, so this will be the bandwidth. So what is the bandwidth? The bandwidth is 400 hertz. Here also bandwidth is 400 hertz, but that too aliasing effect will be there because it was not sampled what it is required. It is sampled less than the actual sampling rate. Here it is 300, due to which intersecting of or the aliasing effect will come into picture. If it is sampled at this particular rate, just it will touch with each other. That means what we have covered, Fs is equals to 2Fm, that is this. Fs less than 2Fm, that is this case. Now Fs greater than 2Fm means this will not touch with each other, rather than a small guard band will be introduced in that particular distance between one spectrum with another spectrum. Okay, so this is the analogy behind the given question. So there is one more question regarding sampling. So as it is given, a signal G of t consists of two frequencies components F1 is equals to 3.9 kilohertz and F2 is 4.1 kilohertz. In such a relationship, that they just cancel each other. G of t is sampled at a interval t is equals to 0 t to t where capital T is 125 microsecond and G of t is equals to cos of 2 pi f1 t plus pi by 2 plus a cos 2 pi f2 t plus pi. Here we need to find the value of a and phi of the second frequency component. Okay. So, in this question, G of t is a signal which consists of two frequencies. One is 3.9 kilohertz and one is 4.1 kilohertz. So that means it is called as a multi-tone message signal. In such a relationship, means these two are placed in such a relationship that they will cancel with each other and is sampled at an interval of 0 t to t, and when t is equals to 125 microsecond, and G of t is given as cos of 2 pi f1 t plus pi by 2, and one more component a cos 2 pi f2 t plus phi. Here unknown component is a and phi. So this unknown component we have to identify. So when it is sampled, after the sample, the resultant must be equal to 0 as it is given in such a relationship that they will just cancel with each other. That is, the hint is given. Now we have to identify the unknown component A and unknown component phi. How? Let's see. So first of all we need to sample it. How we will sample? Your T is replaced by NTS because it is sample. Okay. Now what is TS? TS is given as 125 microsecond. So that is also one hint is given. TS is equals to 125 microsecond. Okay. So this is also one hint. So now we need to represent this signal in terms of sample signal. Okay. So let's see. So what are the given data? Two frequencies are given. One frequency is 3.9 kilohertz. F2 is 4.1 kilohertz. Okay, and TS is 125 microsecond. Okay, where G of T is given as cos 2 pi F1t plus pi by 2 plus A cos 2 pi F2t plus pi. So this is the given case and these are the given data. We need to calculate A and phi. So first of all we need to sample it. How I will sample? Let's see. So here I will write G of NTS. So wherever the T is available, you need to substitute NTS. So it is cos 2 pi F1 N into TS plus pi by 2 plus A cos 2 pi F2 N into TS plus pi. Now this is called as a sample signal. Now when it is sampled, it forms such a relation that the resultant will become as a 0. From that we need to identify A and N. Let's see A and phi. So I will substitute cos 2 pi F1 is 3900 into N into 125 into 10 to the power minus 6, that is TS, plus pi by 2 plus A cos 2 pi into F2. F2 is 4100 into 125 into 10 to the power minus 6 plus 5. Okay. Just need to identify the values. So if I will solve this component, I will get cos of 0.975 n into pi plus pi by 2 plus A cos, here n is also available, and this we will get 1.025 n pi plus 5. So this is the resultant value. Now this is the sample case G of NTS. Okay. Now substituting each and every values, we have substituted T is replaced by NTS, TS is replaced by 125 microsecond, F1 is replaced as 2.9 kHz means 3900, F2 is 4.1 kHz means it is 4100. All these things we have substituted. Now we need to calculate the values. First, let n is equals to 0, G of T is equals to 0. Now why it is G of T is equals to 0? Because as it is given, the relationship that they just cancel with each other. Means if you substitute n equals to 0, if you substitute n equals to 1, or if you substitute n is equals to 100 also, your G of T is equals to 0. Okay. So n is equals to 0, G of T is equals to 0. So when I will substitute this condition, okay, in this So g of nt is equals to 0. N is equals to 0 means this whole component will become 0. Cos of pi by 2 is 0. Here we left with a cos phi. Done. This much. Now since a cos phi is equals to 0, here you can see amplitude cannot be 0. Amplitude will be there, but which component can be 0? Phase component. So if I will substitute phi, let us consider phi is pi by 2, then the whole component is equals to 0. So here I will write a not equal to 0, but phi is equals to pi by 2. So this is the first condition. Here we have determined what is the value of a and phi. Always remember, you cannot equate amplitude as 0. If amplitude is equals to 0, means there is no existence of this particular signal. Phase can be 0. Phase, whole component can be tensed as 0 or 90 degree, whatever else, but amplitude cannot be 0. So here I have done a not equals to 0, but phi is pi by 2. If you substitute phi as pi by 2, cos pi by 2 is 0, 0 multiplied with amplitude will become as 0. So this is the first condition where we have determined the value of a and phi. Then we will check for next component if the value of n is 1. That is the hit and trial method. So which you can determine the value of a and phi. And that is the second frequency component we have identified. Second frequency component means n is equals to 0 first, n equals to 1 is 2, n equals to 3 is, n equals to 2 is 3. So now let n is equals to 1. Now if n is equals to 1, your g of t is also equals to 0 for this case also. So what I will write? G of nts, I will write cos of 0.975 n pi plus pi by 2 plus a cos 1.025 n pi plus 5, like this same equation I am writing, only need to substitute the value. If n is equals to 1, this component is 0. So cos of 0.975 pi plus pi by 2, this is the first component. Second component is a cos 1.025 pi plus 5, like this I can write. Yes. Now this cos of this is nothing but a sine, minus sine. So sine of 0.975 pi plus a cos, how much I can write? Pi plus 0.025 pi plus 5, like this I can write. I have separated pi value and 0.025 value. Why I have separated? That is also having certain reason. So it is minus sine pi minus 0.025 pi. I can write like this because 1 minus 0.025 is 0.975 plus a cos, this is cos of pi plus theta. So it is cos theta. Done. So that I can write in terms of pi plus 0.025 pi plus 5. Let it be as it is. Done. Now this particular case, sine of pi minus theta is sine theta. So minus sine of 0.025 pi plus a cos, and cos of pi plus theta is cos theta. So it is 0.025 pi plus 5. Done. Now here it is equal to 0. I need to identify phi and a. Let us consider phi is equal to pi by 2. So if you substitute pi by 2, you will get in terms of sine. So this whole component will become a sine 0.25 pi. Then this is minus sine 25. This is converted into this. Now if you can see, you have already represented this in sign of same term. So take this component left hand side, you will get a is equals to 1. So when n is equals to 1, a is equals to 1 and phi is equals to pi by 2. So this is my unknown values. Okay, if n is equals to 0, a is not equals to 0 and phi is equals to pi by 2. Here a can be plus 1, a can be minus 1, minus infinite to infinite. And since it is an amplitude, we can't say it is an infinite, it is a finite, but it can have positive value as well as negative value. And phi is pi by 2. And here you can see, when I am substituting n is equals to 1, we'll have a is equals to 1 and n is equals to 1. So these are the certain properties of a sampling theorem through which you can determine the unknown factors. Unknown factors means whatever the data is missing in the sample signal, if the condition is given. Okay. So this is one more question regarding sampling theorem. The spectrum of signal x of t is shown below. The signal is sampled, so we have this one. This is x of f 10 minus 10. This is 50. This much curve. This is also this much curve. Then the signal means x of t is sampled. At fs with periodic pulse rate. Okay. Whose time period is 50 by 3 millisecond. Find the sample spectrum. Okay, sample spectrum for frequency up to 50 Hertz. Give the relevant expression for the sample signal. Then very simple. So here this is x of t. X of t is Fourier transform, that is x of f, and it's a band limited signal minus 10 to plus 10. So what is the bandwidth of this modulating signal? The bandwidth of modulating signal is 10 Hz. Then now it is sampled. Okay. So what is the requirement? The requirement of this sampling is 2 FM. So what is our sampling required? Fs is equals to 2 FM is required. So 2 into how much? 2 into 10 is 20. Okay. Now if the required is this, and in this case and it is given the signal is sampled at Fs with periodic pulse train Ts is equals to 50 by 3 microsecond. So here the Ts is equals to 50 by 3 milliseconds. Sorry, it is millisecond. So Fs is equals to 3 into 10 to the power 3 divided by 50 I can write. So it is 3000 divided by 50. So it will become under 60 Hz. Done. So now the required is 20 Hz, but it is sampled, it is greater than the 20 Hz. So that means when I will sample it, there will be some spectrum which will come into picture without analyzing effect. That is the reason that we have to check. So this is the millisecond is given. You need to have converted this in sampling frequency. You need to know whether it is greater than the required sampling or it is less than the required sampling. If it is greater than required sampling, no need to worry. All spectra will come in a adjacent manner without the overlapping of each other. If your Fs is less than the required one, this is the required minimum required. If this is less than this, then the chance of overlapping of a spectrum will be there. Okay. So as you can see, it is 30 millisecond. So it is 3 into 10 to the power 3 divided by 50. So it is around 60 Hz, and that will help us to represent the spectrums without analyzing effect. These are the two hints given. One more important hint: the signal is sampled with a periodic pulse. When the periodic pulse train will come into picture? When the flat top sample signals are there. When the flat top sample signals are available, the additional one function we need to multiply to it. It is a rectangular function. Okay, sampled signal multiplied with your rectangular function, resultant will be the flat top sampled signal. Okay, we need to represent all this. So step by step we will see. So the spectrum for flat top sampled signal, flat top sampled signal. How we can write? We can write S of f is equals to Fs summation n is equals to minus infinity to infinity x of f minus Fs dot h of f. So this is the filter function. Okay, instantaneous function pass through the filter function, you will get your flat top sampled signal. Done. Now what is this h of f? This h of f is the rectangular function, and that you need to represent in frequency domain. That means it is represented in a sinc function. So here I can write t sinc of ft into e to the power minus j by ft. Done. Where t means it is a ts 50 by 3 millisecond, or this you can write 0.053 second. So h of f we will get, substitute this here, 0.05 divided by 3 sinc of f into 0.053 e to the power minus j by f 0.05 divided by 3. So this is my rectangular function. I need to multiply this value here and then I will explain. That is the sample signal, what it is expected. So S of f, Fs is how much? 20 Hz because Fm is given. This T is the periodic time pulse. So it is 20 summation minus infinite to infinite x of f minus 20n because Fs is 20 Hz. So f minus 20n. Then what is h of f? H of f is 0.05 divided by 3 sinc of f 0.05 divided by 3 e to the power minus j pi f 0.05 divided by 3. Done. Now if you solve this, take this 0.05 by 3 into this. So how much you will get? It will be around 1 by 3 summation n is equals to minus infinite to infinite. This is x of f minus 20n and sinc of f 0.05 divided by 3 e to the power minus j pi f 0.05 divided by 3. Okay, so this is my flat top sample signal. Only we need to substitute the value. And how we will decide whether the spectrums are going to overlap or not? Here you can see, here it is sampled at a rate of 60 Hz. But here it is sampled at a rate of 20 Hz. So that means there is no chance of overlapping of spectrum. Okay. Now we need to represent the spectrum. This is S of f. This is f. This is 10. Okay. If you substitute n is equals to 1, the center frequency will become 20. If n is equals to 2, it will become 40. Okay. And the band limited must be 20 Hz. So this is 20. This is 40. This is minus 20 and this is minus 40. One minute. Okay. This is my S of f. If n is equals to 0, you are getting your band limited signal, modulating signal. If n is equals to 1, 20 and minus 20, these two components will come into picture. Now here you can see the bandwidth is 20. Here also you can see up to 50 Hz. So it is 20. It is not voiding the bandwidth. So as per the question, the limitation is about 50 Hz. So we did not to go for n is equals to 3. So for n is equals to 2, the last limitation is minus 50. So it is n is equals to 2, n is equals to 1. So this is minus 1 and this is minus 2. So like this, questions will come in your external exam. which you need to understand what it is given. According to the given question, you need to substitute the value, you need to identify the sample signal, and then most important thing, you need to sketch this structure. It is most important thing. Okay. So for today, the numericals of sample signal is over. We will continue with time division multiplexing, which is the one more important part of your module 4.